Okay, today's lesson is section 3.3, Measures of Position. So this is the third of 4 sections in chapter 3 that we cover. So measures of position. So we've talked about measures of central tendency. Obviously, they describe where the center of a set of data is. And we've talked about measures of variability, which talk about how variable a set of data is. So this one, we're going to talk about measure of position. This is not looking at the whole set of data, but we're going to look at where one particular piece of data falls in a distribution. So that's what the measure of position is. So as we look here, a question that this would answer if you look at this little supposition. Suppose a student got a 75 or 65 points, so not necessarily percent, but 65 points on a bio test, and he had a friend that got 50 points on a Spanish test. In relation to the other students in their respective class who did better. And to answer this question, we have to standardize a score. So we don't know without knowing information about the other students. So we want to figure out where you place in your class. And to do that, we use a standard score. So this is called a standard score, or more often referred to as a z-score. And the z-score is simply the number of standard deviations. So number of standard deviations that a data value falls. So they use the word falls a lot, or a data value is above or below the mean. So pretty simple. How many standard deviations? Was I one above the mean, or a half a standard deviation below, etc.? So in general, to figure that out, how many standard deviations am I above or below the mean? We get the z-score. So the symbol is z. I put that little crossbar on my z. We look at it, take our data value, and compare it to, or find out how far from the mean. So subtract the mean from it. So we're finding kind of distance from the mean. So if I'm above it, I'm going to get a positive value here. And then divide by a standard deviation to figure out how many standard deviations there are. So that's the formula. The formula looks two different ways depending on if you're using samples or if you have data from populations. So for samples, we'd be using the Roman letters. We'd have X, that's always representing our data value, minus X bar, and that would be over S. So this would be the mean, and this would be our symbol for standard deviation. And that turns out not to be the way they write the formula on the formula sheet. I'm not exactly sure why, but for populations, we do the z-score, and we're going to have X. So still, they do use X no matter what for just representing a single piece of data. And then we're going to have mu, and then it's going to be over sigma. So again, these both represent the mean, and they're both the same value, and the standard deviation has those two representations. So this one, if you just reference your formula sheet, here we are on the formula sheet. So you know, and they call it standard score or z-score, formulas right there. So most students, because we do use this one a lot, get this fairly easily memorized without even necessarily needing to, but if you ever get a little confused, you can reference it there. Again, you have to know your symbols. So there's your standard score. Okay, so let's go answer this question now. So who did better in relation to the rest of his or her class? And again, we have that same information. We have those individual scores. So we have the bio test. Somebody got a 65, someone else got a 50 in another class. But we would have to know information about the class. So here we have the class mean was a 50, standard deviation 10. This other person, class mean was a 40, standard deviation was 5. So you could do your own thinking about this and go, well, you know, they both were above the mean. So they were both above average. And that's true. But with someone in relation, we looked at all that data laid out kind of further up if we thought about a bell curve. So let's do student A, the bio test. So we're saying 65 compared to 50. So we know how many points above the mean they were. So just subtracting, they were 15 points above the mean. Okay, but looking at the standard deviations, we want to look at how spread out the class's data was. That standard deviation was a value of 10. So this puts us at a 1.5. And that's our z-score. So for the other student, student B, on that Spanish test, 50 minus 40. When we first just look at those two numbers, we would say, oh, well, they were only 10 points above the mean. So it's taking into consideration the center of the data, but we haven't taken into consideration the spread of the data. So divide by 5. So this set of data, the Spanish test, the students on it, more of the data was lumped together. It was less spread out. So we're going to just divide by 5, and that puts the student with a z-score of 2. So if we're looking at kind of like empirical rule from yesterday, where are they landing on their respective distributions? So this one student, if we put that center, that mean was 40, they're 50, just kind of how far out were they from most of the data? They're up at a 2. So they're higher than this other test score. So they would have another, it would be a symmetric curve. This one was actually centered somewhere different, and it was a little more spread out because of that 10. But however that curve, and you don't have to draw curves for all these, but just to give you the idea, they had a 65, and that put them above the mean, but they were up at a 1.5. So we did 1 and 2, 1.5. They weren't quite as far up, kind of in those outer reaches. So therefore, we're going to say that student B has a higher relative position. This number is higher, so this is a higher relative position because of their relative position, because that z-score is simply a higher number. So there's that one. So go ahead and read the next one. If you want to pause, if you're watching this on video for the first time, you might pause. And if you were live in class, I would say, try this one. So let's go ahead and look at this together if you have paused then, or need to see another example. So we have, which is the relatively better salary, $3,000 a month in a country with an average monthly income of $3,400. So we're noticing it, I'm below average, I'm not too happy about that. And a standard deviation of 500. Or I have this other possibility. Maybe I'm someone making $4,500 a month, and an average monthly income in that country is $5,100. So still this person is below average, but standard deviation is 800. So who's doing relatively better? So again, looking back at this formula, data value minus mean. So we're always going to take our piece of data and compare it to the average. So again, as we noticed, as we read this, hey, this one is below average. You should be expecting one below average. I'm on the negative side, and we're going to get a negative value there. So negative 400, but we're going to divide by that standard deviation of 500. So when I divide by 500, so I should get negative 4/5, negative 0.8. So that would be my z-score. So again, it's negative because we're below. And then for the other one, we're going to take this other salary, $4,500, compared to $5,100. And then we have to divide by the standard deviation. So 45 minus 51, we have on the top there, negative 600. So $600 below average divided by 800. So 6/8, 3/4, and as a decimal, so we're just going to have negative 0.75. So then we look at that. Again, what we're really doing is thinking about where all these things lie on a distribution. You could draw it or visualize it if that helps, or just think of a number line. So we wanted to know who was relatively better. Well, we're looking at a number line, negative 0.8. It's going to come over here somewhere. You're further down, right? So there's 0. Here's negative 1. Negative 0.8's down here. Negative 0.75 is there. So again, on that scale of how, I want to know where I am in reference to everybody else. The person's doing slightly better, still below average. This is slightly higher, so relatively better. So that one is relatively better. So again, you may or may not have picked it initially. Sometimes the results are surprising. Like before, maybe you thought, oh, he has a lower score. He's only 10 above the average, but relatively better when we take into account the standard deviation. And again, here, this person was $600 below, but it was not the only thing to take into account. So that's a z-score. That is all there is to that formula. Some things just to recognize. So let's take a look at these notes. Okay, I think we had a little recording issue there. So we are picking up with some notes about z-scores. So they're comparing two unrelated statistics. A z-score tells you the relative position. So we're looking at where something is on that normal curve. We have a mean of 0 and a standard deviation of 1. So whatever the mean was, when we change it to a z-score, it gets a numeric value of 0, and the standard deviation becomes 1. And if a z-score is positive, then the score is above the mean, and the z-score is negative, the score is below the mean, and if a z-score is 0, then the score is equal to the mean. So those are just some key things to remember. On the flip side, or next page, we're going to look at the fact that sometimes we have to work backwards. So sometimes what you have is you are given a z-score and you're asked to find a corresponding data value. So you have to be given a little more than just the z-score, but just in general, when you do this, there's two approaches to it. So number one, so you can use the formula. So use the formula and work backwards. So use formula and kind of use algebra to work backwards. So we're going to look at that. So we would have z equals, I'm going to use the one on the formula sheet, x minus mu over sigma. So this would be the idea that we are given a z-score, and we have to be given these two things. And our question this time, instead of having an x, would be we have to solve for that. So you can just every time set it up that way and do a couple algebra steps. Or you can think about what a z-score means. So if you think about what a z-score means, you can kind of work your way through these, and I'll show you what I mean, and you kind of come up with your own formula. So let's look at this first one. We have a z-score 1.5 on an exam with an average of 85 and a standard deviation of 4. And we want to know what score corresponds to 1.5. So if we have a z-score, if someone has a z-score of 1.5, so again, thinking of that normal curve that were just zeros in the center, a 1.5, okay, is over here above the mean. We know it's not all the way up in the tail if we think about empirical rule. We're not way up toward the tail, but 1.5. So we're somewhere here, we're above average. So I'm above 85. So I have that much information. So one option is to put down 1.5. That was somebody's answer when they did this formula, when they took their data value, which we don't know, and they compared it to the mean by subtracting, and they divided by the standard deviation. So you can look at it this way, and then you'd have to go, okay, how do I solve for x? So back to some algebra skills, I'd multiply both sides by 4. So 1.5 times 4 and come up 6. And that's x minus 85. And let me add 85 to both sides and get x is 91. So that is option 1. And you can do that every time you have a formula, 2 steps to solve it. Or option 2, you're going to end up doing the same thing, is more to kind of go with what the z-score means. Oh, I'm 1.5 standard deviations above average. So z equals 1.5 means 1.5 standard devs above, because it's positive, so above the mean. So just go, okay, well, the mean is 85. And I have to go up, so I'm going to add 1.5 standard deviations. And a standard deviation is 4. So look at what we're going to end up doing. We're going to end up doing 1.5 times 4, which we did over here. And there's our 6. And in the end, 85 plus 6, and we get 91. So either way it works. So let's do, kind of pause maybe, try B if you want. I'm going to just kind of go through these and see what you come up with. So see what you like. I'm going to just do this one. I personally like the just kind of thinking about what a z-score means. And that's really where you kind of want to get with z-scores. But we're going to see them throughout the course. This is another thing from this chapter that keeps coming up. So a z-score of 2.5, again, it's positive. I'm recognizing that's telling me this person's position was above average. How far above average? Well, 2.5, this is a reference to how many standard deviations, and a standard deviation is worth 4. So I'm going to say, oh, the mean was 85, and this person was 2.5, not points, but 2.5 standard deviations above average. So just stick that in your calculator. You can do it as 1 step. You can do it as 2 steps. And so we're going to be adding 10 here. So that's 85 plus 10, or 95. Again, I'm getting a number that's above average. I could go back and put in the z-score formula and do it. So that's that option. And again, if not, you would have to just put the 2.5 here and solve. It'll work the same way. So let's look at a negative one. Again, what does that tell you if it's negative? I'll go ahead and go through it the algebraic way. So a z-score is -5. My only formula for z-score was, again, from the front of the worksheet, z equals x minus mu over sigma, if you want to use that one. So I could fill in -0.75 85, and then get that answer divided by 4. You're going to see -0.75 is the z-score. So that was that one. Again, the other way to think about this was just a z-score of -0.75 means I'm -0.75 standard deviations below because I'm negative. So below the mean. So I could have just started with the mean, said, okay, I have to move down. So I'm going to take away 0.75 standard deviations. Again, standard deviation being 4. So 3/4 times 4, there was our -3. And 85 minus 3, 82. And you knew that you had to be less than that. So pause. If you're doing this on your own, try it for -2. See which way you like better. So, and as you take a look at that, if you have unpause, so we're just going to take away 2 standard deviations. So basically 85 minus 8, if you think of it that way for this one, 85 minus, because the -2 standard deviations, so 2 times 4 was 85 minus 8, so a score of 77. So below the mean and 2 specifically. Okay, last thing is we have 3 other measures of position. Z-score really is going to be our focus, but some other terms you should be familiar with. Quartiles divide the data into 4s. And we will see this a little bit in the last section when we look at box plots. We already briefly mentioned those when we talked about measures of not central tendency, measures of variation with the interquartile range. But quartiles, if our data, had a min and max, and so we looked at that data strung out, yes, a min and a max, we would divide it into 4 parts. So we would have our middle, and then we would divide the lower and upper half. And we could call these Q1. And actually, if we were naming them as just strictly quartiles, this would be Q2, which would correspond to the median, and Q3. So Q2, also the median, and what we actually more often call it when we do box plots. And what we're saying is we've divided data into 4 parts. We have 25% of the data in each of those sections. And those sections may be different if we look at them on a scale, depending on how spread out the data is, if we have outliers or extreme values. But that's what quartiles do. So we have Q1, 2, and 3. And then deciles. If you could guess by the root word there, this would divide data into 10 parts. So these are used a lot of time in educational circles. We talk about maybe reading scores for young children and look at what decile they land in. Might be a place that you would see them. So again, if we looked at our data and from min to max, and if we want to divide into 10 sections, we would have deciles 1 to 9. So D1, D2, and I'm just going to put ... and our last one would be D9. And we would have 10% of the data represented in each of those sections. So if we think about that, sometimes the question we like to just ask is what corresponds to the median, where the middle would be on that one. So this would be the median would correspond to D5. So they would be interchangeable. Here was Q2. And the last thing, percentiles. And percentiles are different. These are not a measure of position. So that's kind of the first thing. So it's not a percent, or excuse me, it is a measure of position. It is not a percent. So not a percent, it's a measure of position versus proportion. So measure of position versus a proportion. So proportion, if we want to say, oh, I got a 75% on my test, I did like what parts I personally got, how many points out of the total or whole number of points, where my percentile rank is how I'm doing compared to everybody else. And if everyone else did poorly, maybe a 75 is good. And if everyone else did wonderfully, maybe a 75 wasn't so hot in terms of my rank in class. But we still are talking about percentile has to do with 100. So it divides data into 100 equal groups. And again, we could do like a quick visual of that if you wanted to, but again, we have that idea. We had our data on a scale, we divide it into groups, and we'd have P1 to P99 would be what we use to represent them for percentiles. We would have that the median and P50 would be the same. So if you were at the 50th percentile, you were right there in the middle of the data. You were better than half of the other people in that set of data. So that's a big thing to remember about percentiles. And the last thing with percentiles is we will go back and put them on and look at what's the score for a certain percentile. So the 50th percentile is right there at the median. So just for a little side note, IQ score is 100. So if you have an IQ of 100, you're the 50th percentile because you're right on the mean. But sometimes we might ask, and we look at the 80, let's do that, 115 and 130. And we'll say, well, what percentile are we in if we're up here at 130? What percentile does that correspond to? So we have to be a little bit careful. We said from an IQ score is 100 and the standard deviation here is 15. So I could go down to 85 and go down to 70. Okay, but it within this range was 95. But if I want to know what my percentile rank here is, I would have to go, well, wait a minute, this was 95 here to here, but I'm actually more than the 95th percentile. 95% is in between 130 and the bottom, but what about down here? And down here, if this was 95%, I have 2.5% above me, and I have 2.5% below me. So it actually turns out that 130 would correspond to the 97.5 percentile. So just something to think about where you got to watch out with percentiles versus empirical rule. So we'll play a little more with that next week. You don't have a homework problem like that. So just wanted to mention the other measures of position. Homework totally focused on calculating Z-scores. All right, that's it.